Welcome to Around Space. I'm Ken Miller. Today we're going to be talking about how to use spectroscopy to look for extraterrestrial life. I'm delighted to have with us Dr. Bradford Behr, astronomer and optical engineer. In 1992, he got his bachelor's in astronomy from Williams College, Massachusetts. In 2000, he got his PhD in astrophysics from Caltech. Then he moved to the McDonnell Observatory in Texas for 3 years. And after that, he worked at the U.S. Naval Observatory here in Washington, D.C. In the year 2007, he branched off into the private sector, bringing spectroscopy down to Earth. Welcome back to this table.
Thank you, Ken. As always, it's great to be here.
All right, this is an exciting topic.
Yes, and we should be very clear, a speculative topic. No one's discovered extraterrestrial life via spectroscopy yet, but there was an interesting paper by two astronomy researchers at Harvard who started laying out some groundwork and some ideas for using spectroscopic techniques to look for the signatures, looking for hints of various types of extraterrestrial life.
All right. Now, the search for extraterrestrial SETI, we call it, in the past, we've always looked for radio emissions.
Right, listening for either accidental or deliberate communication from a technically advanced civilization.
Now, in the case of Earth, we have around the Arctic Ocean many powerful radars, which are used for tracking bombers and missiles. And presumably, if somewhere else in the universe there's a Cold War, we too would be picking up powerful radar emissions, right, like we ourselves emit. But this proposal now is a completely different part of the spectrum.
As it were, yes, exactly. Yes. So yes, looking for light patterns, certain color patterns that might indicate either plant life or aliens who are into solar power. Let's talk a little bit first about spectroscopy, get everyone
right
up to speed about exactly what we're talking about there.
All right. Well, tell us, for example, what is the spectrum, and then how do we use it?
Right. So everyone's familiar with the colors of the rainbow. Okay. White light can be spread out by a rainbow or a prism or some other device into all the different colors, and that spectrum, that range of colors, actually extends well past red into infrared, heat radiation, and radio waves, and then down in the other direction past the bluest of blue that we can see are ultraviolet and X-ray and gamma rays. Mm-hmm. This is a continuum. This is a whole range of different vibrational frequencies. We can measure in terms of frequency how rapidly these magnetic and electric fields are wiggling as they propagate through space, or we can also express, measure each of these emissions in terms of the wavelength, how far it is from one crest of the wave to the next. Mm-hmm. So spectroscopy or a spectrum in scientific terms is measuring the intensity, or how much energy there is at each wavelength or each color, if you want to define color broadly, in going all the way from gamma rays up to radio waves. So I think a lot of people are familiar in computer graphics with the RGB colors, the red, yes, green, mm-hmm, and blue. You can make pretty much any color on a computer screen by adjusting the amount of red and green and blue. And the flip side of that is looking at a color of an object from nature, you might be able to describe it in terms of how much red, how much green, and how much blue.
Right.
So astronomers, as well as many other fields of science, do spectroscopic analysis, sort of like those RGB values, but instead of just red, green, and blue, we divide the color range into narrower categories, a very specific color of yellow to be distinguished from a slightly different color of yellow. Mm-hmm. And the wavelength, as I was talking about earlier, is how you describe yellow versus red versus blue What we'll often show is a graph of how much intensity is there at each of the wavelengths that you're looking at.
Okay. Now I understand there's a distinction between an emission spectrum and an absorption spectrum.
Right. Where this all gets interesting is that when light interacts with matter, it passes through a gas or reflects off of a solid surface, or even is emitted by something that's really hot and glowing and putting off light. The photons, the light particles, will interact with the atoms or the molecules in the substance, and a given wavelength, for instance, may reflect more strongly or may be absorbed as it passes through. So our own sun, puts out a nice rainbow of colors, but if you look through a scientific instrument called a spectrometer or spectrograph, you'll see that not all colors are equally represented. There are certain very specific wavelengths where that light is being blocked by the outer layers of the sun's atmosphere. And this is how we know what the sun is made of. Some of those lines are due to hydrogen, some due to helium, some due to iron, calcium. All the other elements in the periodic table each have their own characteristic fingerprint, or specific wavelengths that they will reflect or block or emit.
So we can get an idea of the chemistry of a distant star.
Yep. Distant star or any other astronomical object, really.
The chemical makeup. That's amazing. Now, I understand if we're going to be looking for extraterrestrial life, we would expect them to be living on planets.
That's the assumption.
Right.
There are certainly all sorts of imaginative, even scientifically valid alternatives to planet-based life. But our own personal bias, and I think most of the people who are researching this seriously realize we are biased towards life as we know it, living on a planet based on liquid water, even specific molecules. But a lot of using spectroscopy to look at the chemistry of the universe as a whole, things are pretty similar wherever you go. The same proportions of, roughly, the same proportions of the chemical elements, and a lot of the amino acids that make up life on Earth we've found floating in gas clouds on the other side of the galaxy. So it is something you need to be careful about, assuming that extraterrestrial life will be exactly like life on Earth is, of course, ridiculous. But it will probably have some similarities.
So again, thinking spectroscopy, there'll be some kind of an emission spectrum that's radiated out of the star.
Right.
It strikes the planet, and then some of that's going to get absorbed, and then what's left is reflected.
Right.
So it's a little complicated here.
But yes, we're essentially putting all wavelengths, all colors, shining on the planet, and then depending on what's on the surface of that planet, some of those wavelengths, some of those colors will be reflected more strongly than others. And looking at that reflectance spectrum is what this particular paper by the Harvard folks is all about.
All right. Now, if we assume there's life on the surface, let's start with vegetation.
Okay. Yes.
We would expect that this life would try to energize or fuel its growth with the light from the neighboring star.
Exactly.
So we would expect
something akin to the photosynthesis that all plant life on Earth engages in to generate energy and create its own food from the solar radiation.
So it would be perhaps too much to hope for chlorophyll elsewhere.
Maybe not. Chlorophyll is very widespread on Earth. There's certainly no guarantee that chlorophyll, this molecule that's good at absorbing certain wavelengths from our sun, no guarantee that would have independently evolved on another planet, although it could have. But to your point, I think it's likely that something like chlorophyll, maybe some different molecule that is just right for that particular type of sun, You know, if it's a smaller, redder star, then that molecule may have evolved to be more sensitive to the redder wavelengths in the spectrum, and conversely, a brighter, hotter, bluer star, maybe the chlorophyll analog would be absorbing more of that ultraviolet light.
All right. So we would expect to see some, in the spectrum, we see some big, almost bathtub-shaped areas,
right,
where
big dips where the
absorption is taking place.
Absorption and that solar or stellar energy is being turned into useful energy by the plant. But for taking the case of chlorophyll, the reason most vegetation looks green is due to just a quirk of the chlorophyll molecule. It will absorb a lot of the light that hits it, but there's this little bump in the reflectance spectrum around 500 nanometers, which is a wavelength corresponding to green. That's what we perceive as green. So this slight rise in a graph of the reflectivity of plants is something we see as green, but a spectrometer would see that and say, oh, okay, that may be a signature of chlorophyll. Even more telling, if our eyes were able to look just a little bit further to the red, past red into the infrared, there is this huge rise in the reflectivity. It's called the red edge. And that is very distinctive of chlorophyll-based plants. And in fact, it's used, spectroscopy is used in, for instance, from airplanes flying over agricultural land. You can scan and get a sense of the health of the vegetation by how large this red edge, this reflection feature is.
So if the crops were blighted, you would expect less of a red edge.
Exactly, and it's basically a way to quantify, to measure just how green it might. I mean, you can eyeball it and get a rough estimate, but there's a lot of additional information that you can measure with a spectrometer to tell how healthy your plants are and whether the back 40 needs a little more fertilizer, a little more water. That's a whole separate topic that spectroscopic agriculture is a real big deal and a very lucrative business now to give farmers insight into their crop health.
Yeah, I think also in terms of the way nations jostle against each other, we try to get estimates of the crop yields from each other and our own.
See if the North Koreans are going to be extra hungry this year due to unfortunately, they often have crop failures that affect their population. Yeah. So yeah, there are strategic reasons to do this as well. So from satellites and even further afield, if we want to start getting a handle on our supposed possible alien neighbors on other planets, using spectroscopy, once a planet is discovered, then with proper telescope instrumentation, you could, in principle, look to see if there is a red edge indicative of plants on one of these planets.
Now I understand, because I read the paper that you recommended, that there is the possibility that we could detect in a technically advanced civilization, not just a planet that is covered with greenery, let's say.
Which may or may not mean any animal life. We're not suggesting that greenery means farmers. It may just be that, but
just grass.
Right. So looking for this chlorophyll red edge is an idea that's been around for some time. But what was interesting and novel, at least as far as I'm aware, about this recent paper was pointing out that there's a very similar sort of spectral pattern or edge characteristic to the silicon that's used in solar panels.
Right.
That in order to generate energy, electricity from sunlight, these solar panels will absorb some wavelengths and reflect others. It's due to the band gap, what's going on at the atomic level within this semiconductor substance. So
it absorbs a particular band of the sun's light, turns it into electricity, and the rest would be reflected.
Right, and that there's a very sharp edge instead of at the red side, down in the ultraviolet. Depending on how the silicon is configured and how it's doped, that is, other deliberate impurities are put in to give it certain characteristics, you'll get different spectral patterns. So what these researchers are suggesting is maybe we could find that particular spectral pattern in the light reflected from an exoplanet, a planet outside our own solar system.
Now this would be assuming that some significant fraction of the surface were paved, if you wish.
Exactly. This
with
is
solar cells.
This is a civilization that is somewhat more advanced than ours, and maybe in a sort of window where they have a lot of solar power capacity, but haven't yet invented something more exotic of fusion power or any of those other types of power. So they were certainly making assumptions that these alien folks would be interested in generating most of their energy, of their electricity through solar power. But and you can imagine scenarios where maybe not their home planet, but they've found some airless moon or a planet like Mercury in our own solar system and set up huge solar arrays to be beamed back to the home planet, or even big orbiting solar arrays. But the basic concept is, yes, you need millions of square kilometers of solar panels to have any appreciable signature that we could detect from Earth.
Right. Now, perhaps one question is, why silicon?
That's a very good point. There are certainly other ways, even more efficient ways to generate electricity from sunlight, but they all rely on rarer elements.
Gallium arsenide.
Gallium arsenide is one.
I think the cost per square meter is maybe 100 times that of silicon.
At least here on Earth.
Yes.
And maybe our imaginary alien friends live on a planet where those particular elements are much more common than on Earth. But as we were commenting earlier, spectroscopy shows us that by and large, the same materials and the same proportions are found throughout the universe, at least throughout our local area of the Milky Way. So yet another assumption, but a fairly justifiable one in this paper.
Well, it does seem plausible because when a star burns, it produces heavier elements.
Right.
And pretty much they all work the same way. They have the same physics.
Right.
And then at the end of their life, they detonate. Right? And there's a strong nucleosynthesis that takes place, and these heavier elements are then ejected out into space.
Right. So both fast and slow methods. So the supernova explosion and ejection that you're talking about generates some of the elements on our periodic table, while others are formed more gradually and in the outer layers of a red giant are very gradually emitted, but sort of ejected into interstellar space, eventually to be incorporated into a new generation of planets and maybe life. So yes, it's a bit of a truism now, but we are made of stardust.
Sure.
Carl Sagan and many others have said that, but it is literally true that.
So we would expect silicon everywhere.
We would expect silicon everywhere, and it is much more common. Along with oxygen and nitrogen and carbon, are among the most common of the elements when you look at the it's called abundance analysis of stars, and we're just now getting to the point where we can look at the planets themselves to see what they're made of.
Okay, let's talk a little bit about the kinds of stars we'd be looking at. I think in our neighborhood, 80% of the stars are red dwarfs. And
right, smaller and cooler than our sun.
Right, which perhaps helps with the observation, maybe. If you're going to look for planets, how do you do that with the glare?
So yes, there are a number of different ways to detect planets, and most of the planets we know about nowadays are detected indirectly by looking at the wobble. Again, spectroscopy. Looking at those spectral lines as they shift back and forth.
That's a Doppler effect.
The Doppler effect, it's called. As the planet goes around the star, the star goes around the planet ever so slightly. They're actually both orbiting the center of mass of the system, and that motion can be detected in the very subtle shift of those spectral lines. But for measuring a reflectance spectrum of a planet directly, we would want to block the light from the star using a device called a coronagraph, creating an artificial eclipse inside the telescope.
Okay.
And then that would wouldn't totally eliminate the glare, but reduce it to the point where you can see the reflected light from the planet more clearly.
Okay, good. I think there's also like a kind of a transit effect. If the planet goes behind the star, you might see like some kind of a dip, or
and perhaps a cyclical pattern, as you were saying. If this solar farm occupied the one entire side of the planet, and in some of these cases, particularly around smaller stars, we would expect the planet to be tidally locked.
So it shows the same face towards the star at all times.
Exactly.
Much like the moon does.
For the Earth,
Yeah.
right. That
Okay.
the moon used to be spinning more rapidly, but because of the Earth's gravity and the tidal effects, it gradually slowed down, and now we only see one face towards us. And the same thing would happen with a planet very close to its sun, and for a star like our sun, that would probably be too hot for life, at least as we know it. But these smaller, cooler M dwarfs, the so-called Goldilocks zone, the distance at which liquid water would be present, is much closer, and so this planet with solar panels might only have, obviously they're not going to build.
Well, the sunny side you would put the solar cells. Then I guess there's almost a sunset or a ring.
Permanent sunset or sunrise.
Right. There's a ring of green, where the sun is just above the horizon, and then the backside is dark. Presumably, you're then shipping your power and heat to the back to support a much bigger population.
And that is another spectral signature that these researchers suggest. It is possible that a silicon-like spectral pattern could be made naturally by certain types of minerals. But if we saw that spectral signature of maybe solar panels, and then also saw a spectral or even direct imaging of the dark side of the planet emitting light, emitting heat more than you would expect, maybe that's all of the aliens huddled around their space heaters that are being powered by the dayside solar array.
Oh my goodness.
Now, so it's definitely like I said, speculative.
Yeah.
But what makes it, this was published in an astrophysical journal because it makes testable hypotheses.
Okay. So let's talk about telescopes now.
Yes.
Because if we're going to test this, we need a telescope that can do the job.
Right.
What do we got coming up?
So yeah, none of the signal that we'd be looking for here, the spectral signature, is still going to be extremely faint, and even the James Webb Space Telescope that's launching soon probably is not sensitive enough to see these signatures. And as I am now remembering,
an infrared telescope.
It's looking sort of the wrong range of wavelengths, at least for these visible and near infrared features in the spectrum that we're talking about. So
what do we got coming up that's going to launch?
There is a telescope hopefully launching in the mid-2020s called WFIRST, the Wide Field Infrared Space Telescope, which is still largely in the infrared, but is going to look at some of the wavelengths that perhaps chlorophyll and perhaps silicon solar panels would be emitting at or reflecting at.
Yeah.
And that they do a rough calculation to estimate that we could possibly see a solar panel signature or a chlorophyll signature in a planet orbiting Proxima Centauri, which is the nearest star to Earth other than our sun, about 4 light years away, and it's one of these red dwarfs that we're talking about.
Right.
There is a
Proxima Centauri B.
Yes, the lowercase b would refer to the planet.
Yeah.
There is also a proposed sort of back of the well, it's a little more than a back of the napkin sketch, but
concept study.
A concept study for something called, I'm probably not pronouncing it right, but Lavoier's Large Ultraviolet Optical Infrared Space Telescope, which would be much bigger than anything we've flown to date. They're talking about 8 to 18 meter diameter telescope, and
enormous.
Enormous, and it's going to do, not all the wavelengths, but a whole lot of them. Everything from the ultraviolet to the infrared, which would be a huge engineering challenge. If we fly something like that, it would be a marvelous machine that's going to show us all sorts of new perspectives on the universe, and that is large enough and covers enough wavelengths that not just Proxima Centauri b, but perhaps more distant planets, once discovered, could be analyzed to see if these biosignatures, both natural and artificial, are perhaps present.
So it looks like maybe in a decade or two.
A decade or two, we may have some initial scouting reports of the nearby neighborhood, and after that, we'll just have to see.
All right, thank you very much. And thank you for joining us here at Around Space. That was Dr. Bradford Behr talking about how to use spectroscopy to look for extraterrestrial life. Thanks for joining us. See you next time.
But we